Welcome to This Explainer. Today, we're uncovering the invisible, highly dynamic forces right beneath our feet and exactly how engineers manage to tame them. Have you ever stood near a construction site or felt the rumble of a heavy truck driving by? You feel the ground literally shake, right? We'll take that everyday experience and multiply it by 1,000. That's the wild world of heavy industrial machinery and the elements of soil dynamics and machine foundations that we're exploring today.
Imagine the rumble of a subway train and then scale that way up to massive industrial machinery. We're talking giant turbines, enormous drop hammers, and high-speed rotary engines running 24/7. So how does the surrounding infrastructure actually survive all that constant shaking? Why doesn't a factory literally vibrate itself into a pile of rubble? The answer lies in a highly specialized, absolutely fascinating branch of civil engineering. So, let's kick things off with Section 1, the basics of soil dynamics.
All right, let's establish some fundamental ground rules, pun totally intended. We're looking at a field that bridges the gap between static dirt and violent motion. Now, traditional soil mechanics usually looks at static loads, like the dead weight of a building just sitting there. But soil dynamics, that's a relatively new area of geotechnical engineering that goes way beyond that. It focuses on what happens when forces are actively moving, shaking, or impacting the earth. It's literally the study of how soil behaves when you hit it, shake it, or subject it to continuous, rhythmic pounding.
So where do these dynamic forces actually come from? Well, they're everywhere. You've got violent, natural forces like earthquakes, or transient forces like heavy winds and running water. Then there are the man-made ones, engineered blasts, pile driving, even an aircraft landing. But the primary, constant source of dynamic loading that we're really zeroing in on today is machinery. Different kinds of heavy machinery induce totally different types of dynamic forces. Some are rotational, some are impact-based, and they all require highly specialized engineering so they don't just destroy their own foundations.
Moving on to Section 2, danger when soil shakes.
Okay, what actually happens to the dirt beneath us when it starts vibrating? Let's see how this dynamic energy can build into a literal disaster if it's left unchecked. It's basically a chain reaction. When dynamic loading hits, it imparts kinetic energy right into the individual soil particles. First, the soil greens slip and slide, filling up the empty void spaces in the ground. This is called densification. And sure, that might sound relatively harmless, but it actually changes the soil's modulus of elasticity and its bearing capacity. The shock reduces internal friction and adhesion. But here's the truly terrifying part. If you have saturated fine sand or silt, those vibrations can cause the pore water to try and escape. This leads to something called liquefaction. The solid ground literally becomes quick. It behaves like a liquid, leading to massive, sudden instability. Not exactly what you want under a multi-ton machine.
To visualize this danger, engineers map out strict safety boundaries. If you look at the bottom left here, you see vibrations that are not noticeable to persons. But as the amplitude and frequency increase, you move up through easily noticeable, then to severe to persons, and finally, you cross that critical dashed line at the top right, danger to structures. A machine's foundation absolutely must be designed so its vibrational output stays safely away from that danger zone, absorbing the energy before it can rip the surrounding concrete apart.
Which brings us to Section 3, designing machine foundations. To prevent liquefaction and total structural collapse, we rely on the unsung hero of our story, the machine foundation itself. And trust me, this isn't your average basement concrete pour. Keeping these massive machines stable requires some deep collaboration. See, the responsibility is actually divided. The machine designer, usually a mechanical engineer, knows exactly how much the engine is going to shake. The foundation designer, a geotechnical civil engineer, knows exactly how much the soil can actually take. Until relatively recently, a lot of this was based on empirical guesswork. But today, it is absolutely imperative that these two engineers talk to each other and work in close coordination right from the planning stage. If they don't communicate, the foundation fails. It's that simple.
A successful foundation basically has to pull off a high-wire balancing act with several strict criteria. First up, it has to carry the combined static and dynamic loads without causing shear failure in the soil. Second, any settlement needs to be kept within very strict permissible limits. Third, the combined center of gravity for both the machine and the foundation must align perfectly vertically with the base. Plus, all rotating parts have to be balanced to minimize unbalanced forces. And finally, the two huge ones. It absolutely must avoid resonance, and it must meticulously control the amplitude of the vibrations.
Let's explore those last 2 points in Section 4, keeping vibrations in check.
Let's look closer at those critical margins of error.
amplitude, and resonance. Just how tight are these engineering tolerances? Well, let's ground the theory in some hard numbers. Check out the section for high-speed machinery running at 3,000 RPM. The permissible vertical amplitude is between 0.02 and 0.03 millimeters. Just think about that for a second. An incredibly heavy, violently spinning machine is only allowed to move vertically by 0.03 of a millimeter. If it vibrates by 0.04 millimeters, it's completely failed the design criteria. Now, for lower speed hammer foundations, they might be allowed 1 to 1.2 millimeters. But for high-speed precision, the margins are practically invisible. And this brings us to the ultimate enemy of a machine foundation: resonance. That massive peak in amplitude you see happens when the operating frequency of the machine perfectly matches the natural frequency of the foundation's soil system. If those match, it's game over. The vibrations amplify out of control, leading to catastrophic failure. To avoid this, the operating frequency has to be at least 30% away from the foundation's natural frequency. So it must be either less than 0.5 times or greater than 1.5 times the resonant frequency, just to ensure a safe margin.
So, how do they figure this out? Section 5. 2 ways to model.
To guarantee these microscopic numbers are hit and resonance is completely avoided before a single drop of concrete is poured, engineers use some pretty sophisticated math. There are 2 main approaches here. The first is the elastic half-space theory, developed by researchers like Reitzner and Sung. To pull this off, you need very specific soil parameters: the shear modulus, Poisson's ratio, and mass density. The second approach is the mass spring dashpot model. For this one, the required parameters are the spring constant and the damping ratio of the soil. The real trick, and the main difficulty in all of soil dynamics, honestly, is accurately determining those exact soil parameters out in the field.
To help you visualize that mass spring dashpot model, try not to think of the soil as just static, hard dirt. Instead, imagine it as a giant, reactive mattress. The mass is the heavy machine and its concrete block. The soil underneath acts as a weightless spring that bounces back, while the dashpot represents the damping. That's the soil's natural ability to absorb and dissipate the wave energy over time, just like the foam in a mattress stops you from bouncing forever. By modeling the Earth this way, engineers can perfectly calculate how to safely absorb a machine's endless kinetic energy.
Hopefully, this explainer has given you a newfound appreciation for the meticulous math and design keeping the ground beneath our feet solid and stable. We rarely think about the dirt under a factory floor, but without the incredible collaboration of mechanical and geotechnical engineers and their total mastery of soil dynamics, our modern industrial world would quite literally shake itself to pieces. So next time you feel a machine vibrating the floorboards, ask yourself, just how much energy is the Earth below you quietly absorbing? Thanks for learning with us today.